In chemical reactions, reactants always combine in certain proportions, which we call mole ratios, and that comes from our balance equation. We're able to use a balance equation and the coefficients to predict how much reactant is needed and to predict how much product can be made. You can think of a balance equation like a recipe. It tells you in what proportions or what ratios you have to combine your ingredients, aka your reactants, in order to produce a certain quantity of product. So we're going to use s'mores as an analogy to begin with. We have a balance equation. Our recipe calls for 2 graham crackers, 1 marshmallow, and 1 chocolate. So we're always combining in that proportion. Every time I grab 2 graham crackers, we're going to have to grab 1 marshmallow and 1 chocolate. And when they combine, they make 1 s'more together. So if I know that we start with 8 graham crackers, 5 marshmallows, and 12 bars of chocolate, I should be able to use the recipe, our balance equation, to predict how much product, how many s'mores we're able to make. So we're going to keep a running tally and list the quantities of each reactant that we have available at the beginning. So for graham crackers, we're starting with 8, and I'm just going to draw 8 tally marks, okay, to represent our starting quantity of graham crackers. I'm going to repeat this for the marshmallows. We have 1, 2, 3, 4, 5 marshmallows. And finally, chocolate. $12 bars of chocolate. And according to our balance equation, we always have to grab 2 graham crackers, a marshmallow, and a chocolate. So now we're going to circle sets of s'mores, 2 graham crackers at a time, 1 marshmallow, and 1 chocolate. And that combination makes 1 s'more. So we're going to keep a running tally of how many s'mores we're able to make. And I'm going to repeat this. I'm going to grab 2 more graham crackers, a marshmallow, and a chocolate. That together makes another s'more. Repeat, 2 graham crackers, 1 marshmallow, 1 chocolate. A third s'more is made. Repeat, 2 graham crackers, 1 marshmallow, 1 chocolate. A fourth s'more is made. Repeat. I can't repeat this. I've run out of graham crackers. I have no more graham crackers in my pantry. So the reaction, the production of s'mores has to stop here. And this happens in chemical reactions as well. There's always one reactant that gets completely used and it's 0 at the very end. And once we run out of that reactant, the reaction stops and the production of product also stops. So that one reactant that runs out, we call that the limiting reactant because it limits the quantity of product that is made. So we can construct something called a BCA table. BCA stands for before, change, and after. It gives us the whole picture of what's happening in this reaction from start to finish. So we always want to write down our recipe, aka your balance equation. And then the before row is going to be the quantity that is given to you in the question. How much ingredients do you have available in that pantry? And I like to draw boxes to separate our ingredients from one another. Okay. And also it's helpful to draw rows so you can differentiate between the before and the change and the after. So at the beginning, we had 8 graham crackers, 5 marshmallows, 12 chocolates, and 0 s'mores. And we're going to go through, based upon our picture here, how many s'mores we were able to make. At the very end of our reaction, we were able to make 4 s'mores. Okay. chocolates, we had some chocolates left over, and I'm going to count 1, 2, 3, 4, 5, 6, 7, 8 chocolates remained. Marshmallows, we had 1 left over, and the graham crackers were 0. And because the graham crackers are 0, we identify that as the limiting reactant, the one reactant that runs out at the end of this reaction, and the reaction stops once we have 0 of it. Now for the change row, the change represents the quantity of reactants that are being used and the quantity of product that is being made. Since graham crackers is your limiting reactant, that limiting reactant determines how much of everything else is being used and made. In order to end with 0 graham crackers, we have to subtract all 8 graham crackers. We're using all 8 graham crackers. So if I just focus in on this 1 graham cracker column, I'm starting with 8 graham crackers, using 8 graham crackers, and ending with 0 graham crackers. So I read it as before combined with the change equals the after. And I'm going to put a box around the graham cracker column to really focus in on the fact that this one is 0 at the end of the reaction. It's called your limiting reactant. And its quantity determines how many marshmallows are used. So we're going to copy that 8 all the way across into all the other change boxes. Since marshmallow is a reactant, it gets a minus sign because you're using it. Same goes for the chocolate. But the s'mores are products, so they get plus signs. Okay, so as you see here for the change row, everything's based upon the limiting reactant. The reactants get negative signs. Products get plus signs. And then there's one more thing that's super important. We're going to multiply by a mole ratio, which is essentially the ratio of the coefficients of your reactants to that of the limiting reactant. So looking at your balance equation, the coefficient of marshmallow is 1. So I'm going to put 1 over another number. That other number is going to be the coefficient of the limiting reactant, in this case the graham cracker. So I go to the balance equation, the coefficient in front of graham cracker is 2. So I put a 2 in the denominator. This is the mole ratio. This is telling me for every 1 marshmallow that reacts, 2 graham crackers react with it. And I'm going to repeat this process all the way across to the other change boxes. So for chocolate, its coefficient is 1 over the coefficient of the limiting reactant. The limiting reactant is still the graham crackers. So the graham crackers all the way throughout this reaction, so it's going to be a 2. And I repeat for the s'mores. Its coefficient is 1 over the coefficient of your limiting, 2. So that 2 is the same for all the change, for every single species here, because it comes from the coefficient of your limiting. And you can simplify what you have here in the change box. 8 divided by 2 gives you 4. 8 divided by 2 here gives you another 4, and here as well. And so now when I examine the marshmallow column, I combine its before and change, and it should equal the after. So I have 5 minus 4. Yes, it equals 1. I do have 1 marshmallow left over, or what we call in excess. You have extra. I'm going to check the chocolate column. I started with 12 minus 4, and we're left with 8 chocolates in excess. And then for the s'mores, we started with 0. You're adding 4, and it equals 4 in the end. So we made 4 s'mores. So which ingredient is used up first? go to your after row. The one that is 0 is completely used. That's your graham cracker. And then you do have a few ingredients that are leftovers. Those are your marshmallows and your chocolates. So we can give these formal names or formal definitions in chemistry. The limiting reactant, another word for reactant is reagent. Limiting reactant is the one reactant that is completely used. It runs out first. Runs out first. It's the one that's 0 after the reaction. It's the one that's going to read 0 on that after row. And then the excess reactants or reagents are your leftovers.